Hey, we're going to continue the conversation about planetary transmissions, and we're looking at the two-speed automatic transmission in the notes, and we're going to first analyze for mobility, and then we're going to do the transmission ratio calculation. It consists of a combination of two planetary units where the carrier of the first unit is the ring gear of the second unit. This can be used as a very basic, simple automatic transmission by applying either brake 1 or brake 2 and immobilizing, that is setting to 0 RPM ring gear 4 or ring gear 2, which is same as carrier for the first unit. You get one or either of the speeds. So like I said, we're going to look at mobility first, and we begin with counting the links. So we're having link 0, and link 0 is going to be the ground, and let's assign the number 0 to the, let's see, so I have, hey, copy, paste, okay, so 1, and it will be number, or likewise 1, as well as another one that deserves 0 labeling, which is this one here. Okay. As same as before, we are representing just the top half of the transmission. Planets occur in 3 or more than 3 numbers for load sharing, and again, ground is 0, and then we have for a number of links, I have 1 and 5. That's the same thing, so I'm going to add it here. 1 and 5 is the same, and then let me start over. So it would be 0. Hey. Okay, so let's start counting. So 0, and then we have 1, which is the same as 5. As you can see, they are a single unit, single body. We are having then number 2 as separate body. We're having 3 as separate body. 2 is that's the ring gear, which is also the carrier, the arm for unit 1. Okay, number 4, we have number 6 as a separate body. We have number 7 as a separate body. So together they are 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay, 7. We have 7. Ground link including. And then for joints with 1 degree of freedom, there is 1 here. I thought I chose, so it's 1 here. There is another one here, so 2 so far. And then we have coaxial to the ground. We have several of them, so let's see what the multiplicity of those is. So we have 0, and then we have 1 and 5. 1 and 5. Wow, it's better with the pencil. Okay, so 0, 1, and 5. And then I have also to the ground, I have 2. Okay, to the ground. I have 7 to the ground. And I also have 4 to the ground. Okay, so 0 as well as 1 and 5, 2, 7, and 4. So it would be 1, 2, 3, 4, 5, 6, 7, minus 1, that is 6. Joints with degree of freedom only for 1. And then joints with 2 degrees of freedom, I have for every gear pair or gear meshing, I have 1 of those. So 1, 2, 3, and 4. So it's 4. So mobility now is 3, and I have 7 minus 1, and then I have negative 2 times 6, and then I have negative 4. Expectation is that the number of degrees of freedom is 2, because by engaging one or the other of the brakes, I'm suppressing a degree of freedom. I'm left with 1 degree of freedom. That will be the term of motion corresponding to 1 input and 1 output. So let's see, we have 3 times 6, negative 12, negative 4, and it's indeed 2 as we were anticipating. Okay. So now let's look at the equations that help us calculate the mobility, or rather, I'm sorry, not the mobility, but the transmission ratio, input-output transmission ratio. So input to output is going to be omega. I have omega of 1 and 5, they're the same thing, over omega of 7. Okay. And then since I'm dealing with 2 units, I would need to do motion inversion. I'm going to write a second equation, also motion inversion, that relates the RPM of number 2, which is the same as carrier. But since I use omega 7, I would need to work with this second unit. So, and again, motion inversions, meaning that I have to subtract the omega 7 from the 2. Okay, well, I need to back off. I apologize for this. So let's this would be too straightforward, and is not the way we do it for this particular transmission. Sorry. So we're going to go with the first unit. I'm writing the transmission ratio that goes between 1 and 4, and I'm going to write a transmission ratio between 5 and 2, and then I'm going to relate them, ultimately getting what you saw earlier, omega 1,5. That's omega input. So what I'm interested in is, let me clear some space. So what I'm interested in is ultimately is omega 1,5. That's the input link over omega 7. But before we could get this, I need to write twice equations for corresponding to the 2 planetary units in a motion inversion, that is subtracting the omega of the carrier. So for the first unit, I could write, not that there's the only equation, but overall only 2 are independent for this transmission. So I could write omega 1, and then again motion inversion, so I need to subtract omega of the carrier, which is omega 2, and going all the way to omega 4 minus omega 2. Okay. And in terms of number of teeth, that will be, we've been here before, so it will be negative number of teeth of gear 3 of the planet. Doesn't matter. All it does, it just changes the sign, so it will be negative n3 over n1 times positive n4 over n3. n3 cancels out, so I have n4 over n1. Okay, so this is the first equation that I can write. And the second equation would be, and again, this is omega 1,5. And I can write one between omega 5, which is the same omega 1,5, because the same body. Okay. And motion inversion. So I'm going to body 2, which is the ring gear for the second unit. So, and I'm doing motion inversion, so it'll be negative omega 7 over omega would be 2 minus omega 7. And in terms of number of teeth, I'd also will have the same as above, will be negative number of teeth of 2 over number of teeth of 5. And again, we're doing analysis, so these are all assumed to be known. Ultimately, being interested in this ratio. So using these two basic or equations for the 2 units, how do I get this? Well, it would be a matter of eliminating between these 2 equations, eliminating omega 2 in the first place. But really, the method of solution depends on the configuration. So the basic equations, the 2 basic equations that we have, we would have to make them specific to either first gear or second gear. So gear 1 would correspond to brake 1 being engaged, so I have omega 4 equals 0, and so this is gear 1. Gear 2, gear 2, I wish I had a film on a surface, so there will be omega 2 now equals 0. Alright, so for first gear, you make omega 4 equals 0. You go ahead and say just this, so I have the 0, and I'm going to eliminate omega 2 between the 2 and ultimately get, working with these fractions to get this one ratio in terms of number of teeth. And then for gear 2, I'm going to make omega 2 equals 0, and that will so omega 2 equals 0. That will really correspond to a fixed axle transmission. We could write that from the beginning. There will be motion that goes towards the first gear, but this just not under load. So we could, for the second gear, we could write it right away from the second equation as so I have this equation that gives me omega 1.5. That's the first, or the input, minus omega 7 over negative omega 7, and equals to the number of teeth, and 2 over n5. And what do you do next? You're just saying that, so I could, since I'm using paint, so I could just say this becomes negative 1. Okay, so in the second gear, this is the second gear, you just get the transmission ratio would be negative n2 over n5 plus 1. Okay, so, and for the first gear now, we said that omega 4 is 0, so I make this 0, and would have again to eliminate omega 2 between these two equations, and it shouldn't be that big of a deal. So with this being said, I'm stopping here. Let's go back to the notes and see what else I have. I do have, we haven't discussed this. This is a 2-speed rear axle of a heavy truck. It's it uses a planetary gear, part of the differential, the bevel gear differential for wheel, that's required for wheel turning, and it's able to operate in 2 modes. The normal mode, there is this okay, so like right here I have using a fork running through this groove, I can move this sleeve in 2 positions. And in normal position, I have the planets of the unit and the ring gear, which is this one, connected together. So by doing so, I just block the planetary unit, and it rotates just like a chunk of metal. And between the input coming from the propeller shaft and the wheels, I have just a ratio of a number of teeth of the ring gear over a number of teeth of the pinion, bevel gear. For slow motion, moving on a slope or up an incline or heavy loaded, this sleeve, it's moved inwards until teeth here engage teeth on the housing of the differential, and it shows this configuration. So by doing so, I have the sun gear of the planetary unit fixed to the ground, omega 0, and then the way the unit works is as a planetary gear that has the ring as input and has as output the carrier, the planet carrier. Planet carrier is the housing or the carrier of the bevel gear differential. Okay. All right. This is a one of the early automatic transmissions with 3 speeds, and I have the brake activating table here, first, second, third, and reverse. And for first gear, I engage. So let me take this off. I engage clutch 1 and brake 2. So with clutch 1 engaged, motion goes from the input, so clutch 1 engaged, and then to the sun gear 4. If B2 is engaged, the carry is 0 RPM, so it operates as a fixed axle transmission. So motion goes this way. So transmission ratio is going to be number of teeth of 6 over number of teeth of 4. 5 and 3 they act as idlers. Sign being negative, and negative makes positive, and positive again, so it's positive. Second gear, I have C2 engaged and B brake 1 applied. So with C2 engaged, the input goes to number 1, and with B1 applied, the sun gear 4 has omega equals 0. So this is where the unit operates as a planetary transmission with the flow of motion being in like so. And we'll have to write the motion inversion equations as we learn them. I'm going to post some handwritten or annotated pages with early equations, less the mobility analysis for this transmission, as well as for this one. So again, gear 2 and second gear, it's where the unit operates as a planetary transmission. In the third gear, I have clutch 1 and clutch 2 engaged, so it's forcing gear 4 and gear 1, the two sun gears, to have the same speed. They have different number of teeth. Transmission ratio internally will be different, so this essentially makes it a direct drive. The unit moves as a chunk of metal. So relative to the carrier, there's no motion. So this moves as a chunk of metal. And for reverse, I have C2 engaged and B2 engaged. So C2 engaged, and with B2 engaged again, carrier becomes a fixed, and the transmission ratio now is going to be negative N2 over N1 times positive N6 over N3. So negative and positive becomes negative, and this is how reverse is achieved. Okay. There are many other examples. I haven't analyzed this Simpson, also one of the early automatic transmissions. This one uses a one-way clutch, part of its design. So likewise, two clutches and 2 brakes, and the activation table is listed here. The way the clutch works is the one-way clutch is it allows motion to be go free in one direction, but it's acting as a brake when direction of motion is reversed. One-way clutches are used in automatic transmissions. On one, they are part of the converter unit, and in order to increase the efficiency of the unit, at some point, it's going to take the reactor and the turbine and make them as one unit, and they're also part of the transmission themselves. Some concepts for in general considerations for automatic or rather planetary transmission design. As you can see here, I would have to have the same tooth proportions, that is the same circular pitch for 1, 3, and gear 1, gear 3, and gear 4. Not required on this design because 1 and 2 they mesh separate from 4, 5, 3, and 6. So 4, 5, 3, and 6 they need to have the same circular pitch. 1 and 2 they can be different. The planets are always multiple number, 3 and up. Here we have 1, 2, 3, 4. You cannot have too many of them because they will interfere adjacent planets. And then there is the not any number of teeth for the ring gear, the sun gear, and the planets would allow for equally spacing. There are equations that need to, in integer numbers, that is the number of teeth, they need to be satisfied. I'm not going into detail. And finally, for units like these, I would need to have, so not any number of teeth could go to 1, 3, and 4. Number 3 has to be only a certain number so that it can sit in between 4 and 1, or more specifically, in order to have the same center distance between 4 and 3 and 1 and 3, there has to be a relationship between the number of teeth of 1, 3, and 4. Okay. All right. So this was it. I'm going to switch to part 2 of the notes. Okay. So second part of the notes is on involute gear theory. I may have to change numbering of the paragraphs. Anyway, so teeth in contact are curved surfaces with special properties. We want the transmission ratio between the two gears to be constant. It's one main requirement, and it's expressed by the fundamental law of tooth gearing. We recognize that the instant center between gear 2 and gear 3 is going to be the intersection point between the line of centers, the line that connects the center of rotation of the two gears, and the common normal to the teeth in contact at the contact point. Shown on this graph, it's also represented the velocity of the contact point from the perspective of gear 2 and of the contact point considered part of gear 3. Since they do not overlap, the two vectors have the same magnitude, same direction when the contact point coincides with the instant center. Instant center is also called the peach point. So outside the peach point, when contact point is not coincide with the peach point, there will be some sliding. As shown, gear 2 counterclockwise, gear 3, and I'm seeing some typos here. So this should be gear 3. This should be gear 2. Would have to update this figure. But in any case, outside of when the contact point is not coincide with the instant center with the pitch point, we have relative sliding. So the two teeth can slide towards each other and or away from each other past the pitch point. Anyway, so fundamental law of tooth gearing, and again, instant center theory. When we looked at two moving bodies on the ground, contact between a cam and follower, we had a couple of examples. Should be reviewed at this time. Okay, so fundamental law of tooth gearing says in order to have constant transmission ratio, we will have to have the pitch point or the instant center between the two gears at the fixed location. If this doesn't happen, then the transmission ratio is not going to be constant. Or in other words, we want the common normal to intersect the line of centers at the same point. Further terminology we call pitch circle, the circle centered at the center of the gears through the pitch point. Pitch radii are the radii of the pitch circles, and then I use the term line of center. Center distance is the distance between the two centers. Line of center is the line that connects the two centers. And further terminology will be introduced as we move along. Of main concern to us are the involute gears. These are the most commonly seen in practice. There are others like cycloidal used in clockwork. There are the Wildhaber-Novikov gears used in special transmission, high efficiency transmissions for helicopters, say. But why involute gears? Because they have some outstanding properties that make them easier to manufacture, and also when it comes to operating, they have some favorable properties. So first of all, transmission ratio is not sensitive to center distance. So small variation of center distance called by thermal expansion or fabrication errors is not going to affect the fundamental law of tooth gearing. Other gears, they are sensitive to center distance change. The same tool can be used, either hub or rack cutter or gear cutter can be used to manufacture gears with any number of teeth. We looked at the manufacturing processes, and there was one form cutting that's excluded there. You need a tool for so same tooth proportions, same circular pitch gears. But if the number of teeth differ by one or two teeth at most, then you need a different tool. Here, the same hub or rack or gear cutter could be used to manufacture gears with any number of teeth. Any meaning small number, it's limited, maybe 8, 10, 11, and then 17, 18 if you don't do what it's called addendum modification, non-standard gears. The rack cutter and the hub cutter can have straight cutting surfaces which are easy to generate and to sharpen. Hobbing process is done continuously without reversing the tool, and it's increased productivity, increased accuracy. The other type of gears I mentioned, cycloidal, used in clockworks. There are cycloidal gears used with pin gears, also seen in clockworks or to drive chains. And this is Wildhaber-Novikov. If you look at the, so both are external gears. If you look at the tooth shape, they are concave, convex. And this is a preferred type of contact versus a concave like in involute external involute gears. External gears. So if you look here, we have the contacting surfaces. They are both concave. So being concave increases the Hertzian contact stress. Okay. Think of you wearing on the top of your hat a heavy bowl. Okay, say you have an exercising or maybe I don't know a pumpkin, heavy pumpkin. Put it on your head, and now consider instead of the pumpkin that you're carrying a say a salad bowl. Bigger than your head, yes, but the contact between your head and the salad bowl from to the inside, and as heavy, it makes it more comfortable to carry, to receive the load to your sensitive head skin. Okay, so it has to do with again Hertzian contact stress. All right, so the flanks of the involute teeth are portions of involute curves of for a given gear of the same circle, and this is called a base circle. And how do you obtain an involute? You start with a base circle. How can you practically draw an involute? And you're taking, so this is the base circle. And imagine that you have a ribbon or a string that is attached to the circle. Imagine this to be a like a tin can, and you have a ribbon attached to it. You have it glued, maybe extended, but it's glued. This is where glue ends, and you have a pencil attached at the end of the string or the ribbon, and you wrap the ribbon around. And the pencil, when it's fully wrapped, is at A. And now hold the can fixed, and let's assume that the wrap extends, okay, enough around. I think I started saying that this is where the glue ends. Let's assume the glue ends for past point B. Anyway, so I have the string fully wrapped, and I unwrap it by holding the string taut, and I'm marking on paper, which is fixed with the base circle. I'm marking on paper this curve in red, and this is the involute of the given circle. There are some properties to the involute curve. One is that the length of this arch from A to B, it's equal to the distance between B and C. In virtue of the ribbon or the string being unwrapped carefully off the base circle. Another property is that the radius of curvature of the involute curve around this point or at this point, it's equal to this segment. Okay. So these two. In addition, we have, as you can see, we have because of the 90-degree angle that it's both at B and C, we have angle phi common as shown, and using vector equations, we can derive the parametric as well as the Cartesian equations of the involute, and they are explained here in my notes. So I do have an issue with moving to the new equations system of Word. Anyway, so this is the Cartesian, rather polar equation, the two equations for the involute, and these are the equivalent Cartesian equations for the involute curve. We discussed about gear generation, and we look at just the gear tool used on a shaper machine. The most or the one that's first explained in lectures is using the rack tool. So I'm going to go to my working models. This is the one that you saw last time. Okay, so we have the rack tool, or rather the gear tool, and there are some circles shown. So I have in green, it's the pitch circle of the cutting tool. In green here, it's shown the pitch circle of the gear that will be generated with number of teeth 11. Let's make this 18. There is a coefficient 0 that's set here that's set to 0. Okay, so the two pitch circles shown in green. In blue are we call them addendum and addendum circle, addendum being the circle through the tip of the teeth, the addendum through the root of the teeth. And in red is the base circle of the future gear. If I hit run, what happens is the cutting tool is rolling without slip. The pitch circle of the cutting tool is rolling without slip on the pitch circle of the gear that's generated, and the envelope of the very many positions of the cutting tool is going to generate the tooth. Okay. You saw me. I could also, if I make this negative, I can generate internal gears, and here as well. We do have pitch circle stays unchanged for the cutting tool. I do have the addendum circle through the tip of the teeth of the future gear. This is the addendum through the root of the teeth of the future gear, and the base circle in red of the future gear. Okay. But I started saying that, so I reviewed what we looked at last time when it came to gear generation. So this is, and you may want to also read here, 20-degree full depth tooth, module 1 envelope profile generation. So we're having the cutting tool, which is a rack, and it's a conjugate rack to the one that would mesh with the future gear, because you want to have clearance at the root between the two, either rack and a pinion, or two gears that mesh. You have to have a clearance to allow for thermal expansion, to allow the lubricant to be squeezed out. Other reasons to clear the chips as they get generated during the fabrication process. Okay, so we have this line. This is called the reference line of the generating rack, and the length of the measured between this point and this point on the rack, it's equal to the pitch, rather circular pitch of the future gear. So if I take this length and divide the circumference of the pitch circle of the future gear, I'll get the number equal to the number of teeth. During the generation process, this reference line of the rack rolls without slip on the pitch circle of the future gear. So if I hit run, and of course you can assume an extension to it. So that rolling without slip becomes apparent. So hit run again, reset run, and I'm enveloping the one tooth at a time. Of course, a rack tool may have 3 teeth, and I could start actually I am starting in addition to finishing one tooth fully, I'm starting the flanks of the neighboring teeth as well. Okay, there is I'm also explaining here the addendum modification ideas. So if I have, say, only 11 teeth to the desired to the future gear, and I generate that tooth is going to be undercut. That is, the root of the tooth will be such that the thickness is reduced, and this is prone to failure in bending. There's also something about the involute. The involute curve stops at the red circle, which is a base circle. Inside of the base circle, the curve is no longer an involute. So I'm not having any kind of meshing between teeth. Beyond that, so the remedy is to do what is called addendum shift. So if I make this say 0.25, and what does that translate into? I have this distance added to, or the rack tool is shifted out by the amount of 0.25 relative to the module. So it'll be 0.25 of the module. And now I'm going to see rolling without slip, not of the reference line but of the rack, but rather of a line that is towards the tip of the cutting rack and offset by the amount of 0.25. So now the rolling without slip won't happen relative to this line, but rather a line that is not shown below it, offset by this amount down. So I hit run, and what is the effect? I alleviated the undercut. The tooth became pointed, but it's thicker at the root and stronger, and I was able to get it for 11 number of teeth. So if you want to go with fewer than 17 or 18 number of teeth, which is assumed to be the minimum number of teeth of a pinion or a gear, that the undercut is acceptable and it could operate. If you want to go less than 17 or 18 number of teeth, you need to consider an addendum modification positive type. If I instead make this number negative, I'm exaggerated the undercut. So now I'll have a line that is offset towards the addendum of the cutting tool by the same amount. And now rolling without slip, it happens about this line of so the line that is offset, not shown, tangent to this point, is going to roll without slip the rack relative to the base. The pitch circle of the future gear. So what happens? The tooth becomes even more undercut, and it's of course even less acceptable to operate or utilize the gear with this type of tooth. If the number of teeth is large, so if I make this say 25 and zoom to fit, and then zoom into the area of the then undercut does not happen, and tooth is not pointed, so I could use for larger than 18 number of teeth, I could use negative addendum for reasons of, say, accommodating an imposed center distance between the meshing gears. So I could have that 11 teeth pinion with a positive 0.25 addendum modification. I take the conjugate gear with 25, the one that's meshing with 25 teeth, and I do the negative 25 addendum modification, and now I can have the center distance, the standard center distance between the two gears preserved. So these are the zero shift gears. So overall there's zero shift. The sum of the gear shifts is zero overall, but not individual. Okay, so back to the printed notes. Transmission ratio between gears, we know it's ratio of number of teeth, okay? But it's also equal to, I hope anything will happen. So it's also equal to the base circle radii ratio and pitch circle radii ratio. So this gives the equivalence between a pair of gears with external contact and the friction wheels and the cross bell transmission. And this is also equal to, should have added here, it's also equal to the way you know it. Come on. Oh, it's slower. I would have to do this offline. This is also equal to, this ratio is also equal to, hopefully, just convert it from older equation to new equation, it will be preserved. So it's also equal to omega 1 over omega 2. We discussed about the equivalence between friction wheels and spur gears. The cross bell transmission is added new. And you'll see that the diameter of the sheaves of the cross bell transmission are, the diameter of the sheaves are the base circles, and the friction wheels are the pitch circles. Okay. And friction wheels, they roll without slip. Gears, they don't because of the presence of the teeth. The belt, assuming no slip. So there are the three equivalences to remember. And gear generation with the rack, it's related to the cross bell transmission in a way that I'll explain using this working model. So what you're looking at is the sheave, one sheave and the other sheave of the cross bell transmission. Imagine that pencil now attached somewhere here in between the 2 points of unwrap. So the cross belt or the ribbon gets wrapped around this cylinder, breaks contact, and now it's wrapped around the cylinder the opposite, and I have a pencil here. If I hit run and record the locus of this point with respect to one or the other of the discs, I'm going to generate the flanks of the two teeth in contact. As shown right now, the locus of point C is on a line, the common tangent between the two base circles. However, if I don't know why it's so slow. Maybe because it's running the the recording. Come on. I said stop, and working model is not responding. All right, that's okay. Close the program. And I'm going back to this, and I said now I'm going to view, so new reference frame, and I'm using the base circle 1 as the vantage point. So you're writing on top of the base circle 1, and if we're recording the locus of point C, you'll see that it's enveloping the blue flank of the tooth. So I hit run. Okay, said what's going on? And yet again, close the program. Sorry for this. I clicked on the wrong body. I'm sorry. So I was supposed to click on this. So view, new reference frame, envelope 1. Okay, now I'm good. Hit run, and again the locus was going to locus of C is going to envelope the flank of one of the gears. I stop, and it was easier to just wait for the program, close the program. If I do it the other way, writing on top of envelope number 2, it was this one, and go and view a new reference frame, envelope 2, okay, and hit run, I'm going to envelope the other one. Okay, so how is this related to generating with a rack? Imagine that I also have like a cutting surface that is perpendicular to the string at point C, where the pencil was. And so it will be the 4th time we're restarting this. Okay, so again, let's assume that I have a cutting. I'm using the just for this. What is it? Imposed distance constraint. So imagine, and shorter than my segments, really, but perpendicular to the string, I have a cutting surface, and this cutting surface is enveloping as the back and forth motion that you're familiar now with occurs. This line is going to envelope both of the envelopes in the process. Okay. All right. Now, actually, I need to go back to the same application, and I could increase the center distance. If I'm dealing with a cross belt transmission, that will require the use of a longer belt. Here, assuming the string or the ribbon to be wrapped on the 2 cylinders, I'm just allowing for unwrap on one or on both until the new center distance is accommodated. The meshing action, I could repeat everything that we looked at, and I'm going to generate the same 2 envelopes. Likely will happen in a different, or will happen not exactly. I'm going to with the moving point C envelope other portions of the envelope, but still I get an involute shape to the teeth, and this explains why involute gears are not sensitive to center distance modification. By moving the teeth away or the gears away, the backlash is going to increase. So gear pair external, now I have not just a pair of teeth, but so as you can see, I have 0 backlash. Now I increase the center distance, there's substantial backlash now, but I still have involute meshing or meshing of the involute teeth. And actually gears, the way they are designed, you want to have some amount of backlash to accommodate any possible thermal expansion or the like. Okay, so like right now, these are called zero backlash gears, are considered, although you can see a slight backlash, but that's because of the way the model was done. But the again, the practical gears, you would have to have some backlash to allow for thermal expansion, to allow for any imperfections, including bending, slight bending of the teeth. That backlash allows for the tooth to bend backwards and without forcing against the next pair of teeth that enter meshing. You see here phi equals 20 degrees. That's the pressure angle. We'll discuss about that. You also see here a number. That's the contact ratio, it's called. We'll discuss those in backlash and measure from the for the measure of the backlash. Okay, so if I hit run, the contact ratio is the largest number. I cannot go any shorter center distance than this. It's annoying. I don't know. It was not doing the same last time. Okay. So yet again, if I, however, like the way we found the simulation, so if you hit run, the pressure angle is no longer 20 degrees, it's 23 degrees. Contact ratio went down from 1.4 to only 1.176. Okay. I have the case of internal gearing, also illustrated with a simulation, and let's see, does it respond on the fly? Sometimes it does. So center distance, rather pressure angle 20 degrees, zero backlash, large contact ratio. If I increase the center distance, or rather reduce it now because I have internal gearing, I have some backlash. The pressure angle changed from 20 degrees, and the contact ratio also changed value. That is, went less than 2, the way it was originally. Okay. But when changing the center distance, I should have pointed to the redrawn pitch circles now. So the pitch circles of the gears had to be readjusted to where the contact between them, the pitch point, is dividing the center distance the same ratio equal to the number of teeth to maintain the same transmission ratio. Okay, so essentially we looked at this figure in motion. I talked about pressure angle. That's the angle of the some angle of the generating rack, but a pressure angle, it's measured at the pitch point, and is the angle between the common tangent to the base circles and common normal to the pitch circles when they are at the their contact point coincides with the pitch point. And these are standardized, and again, they are for gears with zero backlash and with no addendum modification. Remember that X value that was changed, we made it negative 0.25 and positive 0.25. So when that's zero and I have zero backlash, the angle, ensuing pressure angle between the two gears is going to be the same as a slope angle of the generating rack. We recognize also some right angles. So we have the right angle here, two triangles that are similar, sharing an angle, and that relates the base circle to the radius to the pitch circle radius. Also recognize that this angle is the pressure angle from simple geometry. So this angle here is nothing but 90 degrees minus the pressure angle, so it means this is the pressure angle because I have 90 degrees here, and likewise on this other here, on this other gear. Okay, so the geometry properties allows us to relate, like I said, the pressure angle to the radii of the pitch circle or the base circle. The generating tool now, I said that generating tool, so it's shown in yellow. That was the reference line of the generating rack, which is the pitch line. Also, if we have a meshing action, and the distance between two successive points, so I have the circular pitch here, and it's the same as the that of the gear that's meshing with, assuming that that gear makes multiple. I could have gear sector where I'm not suppose not essential. The last of the tooth that you're generating to be a full tooth. It can end with a fraction of a tooth, no concern. But otherwise, there should be a correlation between the circular pitch and the diameter of the or radius of the pitch circle of the gear, in order to of the last of the tooth to also be a complete tooth, not a truncated tooth. And I mentioned that the rack angle phi is the pressure angle, and this is it. So, and it's standardized. 20 degrees, it's a standard value, and then other values that you may see are 25 and 14 and a half. Also shown here are the addendum and addendum measured. Essentially, addendum is the height of the tooth from the pitch line or the pitch circle, and the addendum is the difference from the pitch line to the addendum line or addendum circle. Okay. Clearance is the difference between addendum and addendum. You need to have some clearance, I said, to allow for thermal expansion, for clearing the tool. So teeth, after being generated with the cutting tool, oftentimes they are finished with a grinding wheel, and you'd need that clearance. We have the top land, we have the face width, this is the face, the flank of the tooth, addendum, addendum. Addendum and addendum are standardized with respect to the module or the diameter pitch. We'll discuss module and diameter pitch. I tend to, this is just a digression, so tell students that when it comes to gear, envelope gear theory is like watching a mystery. There are very many characters that make sense only at the end of the movie, or maybe if you watch it multiple times. Hole depth is the sum of addendum and addendum. we discussed what circular pitch is, and it's essentially the circumference of the pitch circle divided by number of teeth. And in order to standardize the proportions of the tooth, so in order to mesh two teeth or two gears, they need to have the same circular pitch. And addendum and addendum are defined as multiples of the what is called module or diametral pitch. Circular pitch is not a good measure because it's an irrational number. I take 2 times pi times the radius and divide it by an integer, so it gets me an irrational number. So for that reason, what's standardized is the ratio between number of teeth and diameter of the pitch circle, or diameter of the pitch circle and number of teeth for the metric system. Okay, and further relationship holds, so 2 times r, that's, and then circular pitch divided by pi, or pi over circular pitch. It's the diameter pitch measured in inches and -1 or millimeters. And they are these values are standardized. So for module, I have, you can see here, 1 millimeter, 1 and 2.5, 2, so forth. With the preferred and second not as ideal, and the column continues. So these are the preferred sizes, and these are the secondly preferred sizes. In terms of proportions, you can draw this relationship. Not that any gear in the module system, in the metric system, could mesh with the English system. Maybe accidentally you can find a close correspondence between these two, like with threads. Really, metric threads and inch threads, you're not supposed to be interchangeable. A small diameter pitch corresponds to a large gear. A small module corresponds, rather large size tooth. A big module corresponds to a large size tooth. A small module, small tooth. Big diameter pitch, small tooth in terms of proportions. So other than the pressure angle, the rack angle, 20 degrees, 14.5, and 25, also standardized our addendum as multiply of 1 over capital P, or module, and so addendum, and hole depth and clearance are standardized, with what's in yellow being the most common one. So addendum 1 over diameter pitch, addendum 1 to 5, clearance 0.25. For the metric system, you just replace 1 over P, capital P, with M, and same are standardized. Okay, so we looked at, so module 1, tooth, it means that at the height of the tooth, it's about the size of this crosshair, or cursor, mouse cursor, is going to be 2.25 millimeters. And for metric 8, module 8, I have what would be 2.25 times 8. That's 18 millimeter tooth height. We looked at undercut already, and we looked at not explicitly at interference. So what's interference? Is when two gears generated by whatever process, you want them to mesh, and if teeth make contact outside of the or inside of the base circle of 1, then you can have interference. Of course, if I take the cutting tool and mesh it now with the, or stub it, that is, take off of the tooth and to allow for that clearance, they can mesh because I enveloped the tip of the tooth below the base circle. But in general, teeth that are put into mesh, same module, same diameter pitch, so they are supposed to mesh. But if I have contact made below the inside of the base circle, this is not going to be a correct contact. We looked at undercut. We looked at the way the addendum modification can fix the undercut. I'm not going to go through the process. I mentioned that teeth with 18, maybe 17 number of teeth are assumed to be as standard gears, not undercut. If you go less than 17 number of teeth, they will be undercut. This equation here, which requires some attention, gives us the what would be the minimum number of addendum that for n number of teeth, I would have the minimum was it sign, so it could be negative value. So if n here is 25 like we had, we'll end up with a negative value. That's the this is the minimum number of undercut that you can apply and not have, or rather addendum modification and without having undercut. Okay, so profile shifted gears, if their undercut is other than 0, if there's no gear shift, those are called standard gears. And the final subject is contact ratio. So contact ratio, I mentioned it already, is a measure of how many teeth do I have in contact. So there are instances where when the contact is around the pitch point, there's just a pair of teeth in contact. As the meshing progresses and the contact point goes in one direction or the other, depending on the direction of rotation, I have 2 more teeth starting making contact. So there will be instances when I have 2 teeth. There will be instances when there's just 1 tooth in contact. But you don't want to have a situation where contact is broken between the current 2 teeth and there's not yet a contact established between the next 2 teeth. In order to measure that, this term has been introduced, contact ratio, and it's defined as the length. So we have line of action, the common tangent, and the length of action is between a segment, a portion of the line of action delimited by the addendum circles of the 2 gears. So addendum circle of gear 3, addendum circle of gear 2. If you can measure me this length, and then you divide it by the circular pitch on the base circle, then that's going to be the an average number of teeth in contact. Okay, and this is Z is the length of action, base circle pitch. You can calculate as function of circular pitch and ultimately as function of module or diameter pitch, P, by the use of the pressure angle, rake angle. And there we have it. So this is the equation for the length of action, determined using geometry. So we're going to take the full length from C to K, and then using geometry subtract AC, and likewise on this side. This is all explained here, and can be written using Pythagorean theorem and the final forms of it. If I have rack and pinion set, this is the equation. If I have external internal gearing, here's a sign that's changing. I do have a set of equations that I made available to you. So we're towards the end of the lecture. It was a long one, I realized. So this is a collection of, and you're going to use it for doing any kind of geometry calculations for envelope gears. So read the comment. The lower sign, if there is any, and we have some, including for contact ratio, I said. So there is a minus plus, and for backlash plus minus. If the lower sign is for internal gear and the upper sign for external, the upper sign for external gears, and then standard values for metric and diameter pitches, and actually here there's phi and alpha. So in the SI system, notation used for the pressure angle or the rack angle is alpha rather than phi. Everything else is, hey, come on, symbol and alpha. So I need to make this correction. Okay, so alpha is for metric, phi is for inches. Standard center distance is sum of the pitch radii if they are external gears, difference between them if they are internal. One of them is internal gear, that is which one are two. Operating distance could be other than the standard distance. Pressure angle at pitch point, pressure angle on any circle, circular pitch on any circle, base circle pitch. You're just dividing this by the number of, or circumference by the number of teeth. It was in the text. I don't think I'm not repeating it. The formula for the circular pitch on any circle. And profile shift coefficients. Okay. So if I don't have, if these are 0, then D equals dW. And so the addendum, you can see here, includes a profile shift distance, but otherwise if x is 0, this is 0. Okay, so learn how to interpret these equations. Again, there is alpha instead of phi used in the metric system. Otherwise, the standards are pretty much in agreement. Okay, so we're to do these two problems, and this being said, the chapter is covered. There is here a function involute. Involute of an angle alpha is tangent of alpha. and elsewhere. So invoked function is tangent of alpha plus alpha. I need to also explain this, although it's I think we made or met no, it's not here. Alright, so this being said, I'm going to stop recording. It was 1 hour and 25 minutes, quite a bit of recording. Take good care of you, and I'll meet you online some other time. Bye.